All right. Welcome everyone to the latest episode of Scrubbing the Skies, the webinar series of the Institute for Carbon Removal Law and Policy at American University. As always, I'm your host, Will Burns, and I'm glad you're all joining us, especially those of you in the United States that are joining us despite the fact that we're almost at the holidays. So it's Biochar month for the series. Our last episode also focused on aspects of biochar, and this time I'm pleased to have a couple of co-authors of a new study, as well as a major representative from the biochar sector. Talk about the implications of this study. We all know that if we're going to reach the prodigious amounts of scaling up of carbon removal that the IPCC contemplates in 2040 and 2050 and beyond, we're going to need tremendous amounts of deployment. And one of the questions is what's the potential outside of some of the usual places that we often talk the most about CDR deployment, the United States, Australia, certain parts of Europe. And the authors of this piece today have focused on that very issue in the context of biochar. What is the granular sort of potential for biochar across the world as well as globally? And so we're going to focus on this study, which is entitled Quantifying Biochar Carbon Removal's Global and Country Level Impact, which was published very recently in the journal Biochar. And joining us today are Dr. David Lefebvre, who's lead author of the piece and faculty of Land and Food Systems at the University of British Columbia, as well as Dr. Tom Trebold, who's a co-author and a research professor at the Rochester Institute of Technology's Golisano Institute for Sustainability. And then finally, Wendy Lou Maxwell Barton, who serves as executive director of the International Biochar Initiative. Welcome to all of you. As usual, we'll start with a presentation, actually two presentations, to frame the issues and to talk a bit about the contents of the article. I'll then move on to a couple of questions to seed the discussion, and then we'll move to the question and answer from the audience portion. So I encourage everybody in the audience to start populating the Q&A box with your questions as the presentations ensue, and we'll go from there. And so with that, I am going to turn over the floor to Tom.
Great, thanks. Thanks, Will, and thank you for the opportunity to speak to this group this afternoon. I think Will mentioned the title of the study, but I'll just repeat it. It's Biomass Residue to Carbon Dioxide Removal, Quantifying the Global Impact of Biochar. David Lefebvre is with the University of British Columbia. Wendy Lou Maxwell Barton is associated with the International Biochar Initiative, and I'm a professor at Rochester Institute of Technology. So just to kick things off, what is biochar? That's probably something that's familiar to everybody on the call today, but just to bring everybody up to speed, biochar is a carbon-rich material made by converting biomass at high temperature under low oxygen conditions. And why it's important is that this material is known to resist degradation for hundreds or thousands of years, thus making it one of only a few commercially viable carbon dioxide removal methods. So typically, biochar is made in a process called pyrolysis, which by definition actually is the complete absence of oxygen. And so as shown in the figure from a paper published by Johannes Lehmann, in the normal carbon cycle, where CO2 is constantly circulating between plant respiration and photosynthesis, and then the plant biomass, of course, will ultimately return to the soil as carbon, but then that carbon is broken down and returns to the atmosphere. So the net carbon withdrawal in that baseline scenario is essentially 0%. When we apply pyrolysis, we're now taking part of that carbon and, in a sense, breaking that cycle. So somewhere in the order of 20% of the carbon is now withdrawn from the atmosphere and now stored in a very stable form, which we can either return to the soil as a soil amendment or use it in various industrial applications, which we'll talk a little bit more about later. So the specific objective of our recent study that was just published last month in the Biochar journal was to develop a framework for computing net carbon sequestration of biochar derived solely from waste organic resources. And the novelty of this study was that we've actually applied our methodology at a national level to determine biochar's potential in offsetting emissions in each country. So we did the analysis for 155 countries, as I'll describe in detail shortly. So our methods were to use open data resources. So we relied primarily on FAO stat for data related to biomass, agricultural residues, and forestry residues, and then also the World Health Organization for data on wastewater treatment biosolids. For each of those waste biomass resources that were identified, we determined the mass yield and organic carbon fraction of the biochar that could be derived, mostly relying on literature sources, although we did use some in-house data from our own research. We also assigned a biochar permanence factor, which we propose can be presented as only a function of the average soil temperature of each country we assessed. And then lastly, we computed the net carbon dioxide removal by biochar carbon sequestration. However, we did account for the emissions generated from biochar production and application. So the data that we'll be presenting are net biochar carbon dioxide removal potentials. Of course, in this kind of an analysis, the assumptions are really critical to clearly define. So that's what I'd like to walk you through here. Firstly, the framework may be based on the generalized model that was proposed by Dominic Wolf and co-authors in 2021. And the reference is given there at the bottom of the slide. As I mentioned previously, we included use of only waste-derived biomass. So any greenhouse gas emissions associated with the biomass production are not included. However, we do account, as I said, for biochar production and application emissions. We assume that 30% of total crop residues are retained in the field to maintain soil health, but all residues associated with food processing are available for conversion to biochar. Other biochar effects, such as priming, nitrous oxide, and methane emissions, were not included. We assume that all biochar is produced under anaerobic conditions, that is, pyrolysis conditions, at temperatures of 600 degrees centigrade or higher. We assumed further that all biochar produced is added to soils, and thus we applied the permanence factors in the previously mentioned paper by Wolf et al. In 2021. However, having said that, we're not limiting the application to only soil. We're also assuming that the biochar could be applied in long-term industrial applications, such as concrete, where we assume the biochar is shielded from decomposition. So the permanence factor would be at least as high as the same biochar applied to soil. The next assumption was that biochar is the sole product of the pyrolysis reaction, with any excess heat generated used to dry the incoming feedstock and sustaining the pyrolysis system itself. We assume that for temperature of 600 degrees and higher, and assuming a 100-year greenhouse gas inventory period, the biochar permanence is a function of only soil temperature. And in the paper by Wolf et al., this is clearly outlined in that paper. We further assume that the permanence factor may be computed from a single average soil temperature for each country. And then lastly, the net carbon dioxide removal is based only on biochar carbon sequestration, and we did not include other potential benefits, including such things as avoided fossil fuel combustion, improved crop yields, reduced water and fertilizer use, and so forth. In aggregate, all those other benefits would be expected to provide much greater biochar benefits than we quantified in this study. However, I want to stress again that our main objective was to do this analysis on a global basis and provide a baseline number for all 155 countries considered. So our generalized framework based on all those assumptions can be presented as described in this equation. So the net carbon dioxide removal from biochar carbon sequestration is equivalent to the sum of the product of feedstock mass yield of the biochar produced, and biochar organic carbon fraction, summed over all available feedstocks. That sum multiplied by the single value of permanence factor, also multiplied by the factor 44/12 as a conversion factor from carbon to CO2 equivalent. And then lastly, subtracting from that entire quantity, the greenhouse gas emissions associated with biochar production and application. So to summarize the results, I'd just like to offer these values. We firstly identified 7.37 billion tons of biomass residue feedstocks produced globally on an annual basis. That translates into about 2 billion tons of biochar that could be produced annually, which would then be associated with 2.65 billion tons of CO2 equivalent carbon dioxide removal. The average biochar carbon dioxide removal potential was computed to be 6.23% of national greenhouse gas emissions in the 155 countries analyzed. However, we determined that there's greater than 10% benefit as a percentage of national greenhouse gas emissions in 28 countries. So now I'd just like to show some of the main results in graphical form. This bar chart shows the biochar potential in absolute terms. That is million tons of CO2 equivalent per year. So we see that China is the leading in biochar potential with over 400 million tons. And every country shown here, all countries have at least 25 million tons of CO2 equivalent removal, carbon dioxide removal per year. The bars shown there are based upon Monte Carlo simulations of variations in all of the major quantities, which I mentioned earlier. It's interesting to note that these countries are pretty well distributed globally, with the Americas, Asia, and Europe all being well represented, but it is notable that Nigeria is the only African country that is among the leaders in absolute terms in biochar potential. When we present the data as a share of each country's total emissions, total greenhouse gas emissions, the picture is quite different. Here we see that a small subset of countries, 3 of which are in Africa, actually can achieve greater than 20% removal relative to greenhouse gas emissions. And also, there's a number of countries, both in Europe and the Americas, that show biochar potential greater than 10% of national emissions. Again, the error bars are the output of the Monte Carlo simulation of variations in all the major parameters that went into the model. So even though the global average, as I mentioned earlier, is 6.2% carbon dioxide removal as a fraction of national greenhouse gas emissions, we see that many countries, 28 in all, have greater than 10% impact. And this map just shows the global distribution in the percentage share of each country's total emissions, with the purple and the dark brown being the regions of highest impact. And if we simplify this down into countries that have relatively high impact in green, that is greater than 10%, and those with relatively low impacts of less than 2%, we see that there's really 3 global regions that are highlighted as concentrated regions for high biochar impact relative to national emissions. Almost the entire, or 2/3 of the continent of South America fall into that high biochar category. That's Brazil, Argentina, and Paraguay. And we also see concentrated regions, albeit on a much smaller scale, in Northwestern Africa and Eastern Europe. So to summarize, I'd like to offer a few ideas for path forward. What's the next step here based on our results? First and foremost, we would propose extending our initial biochar framework to national level analyses in selected regions, and focusing on those 3 regions of high biochar impact would seem to make sense. It's important to do this because one really needs to acquire local data on biomass residue production, residue to product ratio, soil temperatures, and so forth, to improve the fidelity of the analysis that we did on a global basis, that is admittedly lacking some of the granularity that would be needed to make decisions on, say, financial decisions about whether or not to move forward with biochar projects. You certainly need to include, as I mentioned before, benefits that we did not consider. This would involve things like avoided emissions from fossil fuel combustion, improved crop yields, reduced water and fertilizer use, avoided methane if you use materials that would otherwise have gone to landfills. Again, if you were able to accurately quantify all those effects, they could in aggregate surpass the benefit of just the carbon dioxide removal from the stable carbon within the biochar itself. And then lastly, we think there's a lot of work that still needs to be done on techno-economic analysis and life cycle assessment so that all the stages of the biochar production and application can be optimized. So everything from feedstock collection and transport, pretreatment, the pyrolysis system itself, of course, but then also biochar post-treatment and transport, and then finally delivery to bankable markets. So with that, I'll just close by providing the links to the open access paper that's available in the Biochar journal, and there's the full reference for the paper if you're interested. So with that, I will stop sharing and now turn the floor over to Wendy Lou Maxwell Bar. Thank you.
Thank you so much. And thank you again to the Institute of Carbon Removal Law and Policy for having us on today to speak. I wanted to tell you very quickly about the International Biochar Initiative. We are a global platform with a little over 600 members based in 70 countries. And we have both members who are within the biochar industry, as well as companies and NGOs that are coming from other sectors that are looking to use biochar to solve problems that they are working on. So to give a little bit more background and context about biochar, I can see from the participants that many of you are already very familiar with it. However, I want to really emphasize that biochar is really one of the most advanced CDR technologies in the world in terms of being the most readily scalable to an industry level, as well as having the lowest cost per ton of carbon removed. And for that reason, and because of the many additional social and environmental benefits that come beyond the carbon removal, biochar is being used in many sectors, again, to solve some really pernicious problems, which include improving soil health. It can be used for reducing methane emissions in agriculture as well as landfills. It's a very powerful remediation technique for heavily contaminated water and soils, including PFAS and heavy metals. It also can be used to generate bioenergy as part of the production, depending on the technology or equipment you're using. And then, of course, there's this whole burgeoning uses of biochar in industrial sectors, including asphalt, the built environment, and concrete, as well as others. As a carbon removal technology, according to cdr.fyi, the website, it is in 2023 making up about 92% of delivered carbon removal credits. So vastly the predominant technology that's in the market. Again, it is very highly scalable and low cost per ton of carbon removed. And of course, it's been recognized by the IPCC as one of the appropriate CDR technologies. I wanted to talk very high level a little bit about what's currently happening on the policy and regulatory landscape. While there may be more bullet points under the US in this regard, I would be remiss if I didn't point out that currently the U.S. market is, or industry rather, is growing. However, we think that the EU market is larger around the industrial scale, and it's growing at about 68% per year currently. And you can research, or you can reference a market research report that was put out by the European Biochar Industry Consortium. And I also want to mention that that IBI, as well as the US Biochar Initiative, are currently conducting a market research survey, and will have a report out in February of 2024. So just to go through these different points from the US, there is a relatively new source of funding that is essentially paying farmers to use biochar and compost, providing a much needed revenue stream for that. There's a new group called the US Biochar Coalition, which is an industry lobbying group, which has been working at the US Congress to include biochar in the Farm Bill. There is a bipartisan Biochar Research Network Act. There's another bipartisan bill under consideration to establish demonstration projects at every U.S. Forest Service station, which would be a really beneficial thing, particularly in the U.S. West, with all of our biomass in the forest problems for massive forest fires. At the state level, we are seeing either investigation about biochar or actual funding for research projects in those states. And then there are city level projects, including a project funded by Bloomberg Philanthropies that's using biochar production as part of a circular method to use municipal tree or park waste to create biochar that can then be used to improve soil in those places. There's, generally speaking, of course, and this is admittedly a very, very high level overview of policy, I want to point to some very good resources that Carbon Future has on their website, and which I used as reference. Just to point that currently only Denmark and the EU has biochar as part of its carbon removal goal, and a quite ambitious one at that. I did want to point out a miss for biochar in that it is not included in the US 45Q tax scheme or in the Inflation Reduction Act as a specific carbon removal technology. So of course that is a missed opportunity that we hope to not have in the future funding options. I would say also that what we hope for the biochar industry is, in terms of regulatory and legislative support, as well as funding, is not very different than any other industry that's trying to grow, in that we'd like the support of tax incentives, public procurement that point to biochar, as well as funding streams that can help to develop the industry. So I'll stop there, and I guess we'll move into questions.
All right, thank you very much. And yes, we'll now move into questions. So just a couple of questions that I would ask, and then we'll move into to audience questions. So first question for Tom. So in the methodology, you indicate that in assessing the ultimate sequestration potential of biochar, that you leave 30% of the crop residues on the land to ensure crop health, but that all of the other residues in terms of food production are assumed to be used in biochar. But my understanding is that a lot of times crop residues are used in an array of manufacturing products, as well as animal fodder, fertilizer, and bioenergy production. Do you think those should be taken into account and potentially reduce the potential, or am I just reading this wrong?
No, I think certainly, Will, all those existing uses of biomass residue absolutely have to be taken into account. I think that speaks to the need to do a much more detailed, much more granular analysis at the level of individual countries or regions. But I do think that question depends largely on the level of development in certain economies. I think in more developed economies, we've already started to identify potential uses of those materials in some of the areas you mentioned. But I know for a fact that in many economies, probably more on the less developed side, there's a lot of material that's just unused. And one example that comes to mind is cocoa pods. And I know about this because I have a student, a former student from the Ivory Coast, which is one of the major cocoa producers. And he just says he's so interested in this as an opportunity to make biochar, because there's just mountains of these cocoa pods that are left in the field to rot or they're burned. And we know that makes very high quality biochar. So I think there's opportunities, but in short, yes, those existing uses have to be taken into account, but that speaks to the need to get down into the next level of detail on the analysis that we've published.
Thanks. Yeah,
And
that's one of the things. Oh, go ahead, Wendy Lou.
oh, sorry. No, I just wanted to sort of double down on Tom's point about crop residue burning as well, because we know that this is a really prevalent practice in many places that's contributing to pretty major air quality problems and other associated health issues, not to mention the lost opportunity to create biochar. So it's just it's something that would be such a better alternative in many places if there were to be development and funding to provide farmers with the know-how and the technology to do it.
Thanks for that. Another question I had is one of the things that you consider also is wood chips and recoverable wood products, right, as potential feedstock. I know that the bioenergy with carbon capture and sequestration industry would like to have those resources also. Do you think this is a better use ultimately from a standpoint of sequestration or other aspects of life cycle assessment, or is that something that we also need to be looking at in the future?
Yeah, so I think all of the carbon dioxide removal strategies, and I believe there's 8 of them that are at TRL level of 6 or higher. I think all of those have to be in the toolbox, so to speak. Certainly bioenergy with carbon storage, carbon capture and storage is becoming or is currently commercially viable. But I think we would argue that biochar has some unique advantages, mostly from the standpoint of co-benefits. Right? Making biochar, we're offering the ability of improving soil health, making that material opens a lot of opportunities for industrial applications. That's kind of what I focus my research on. We've mentioned things like concrete, but there's a lot of other industrial uses of biochar that we're focusing on. And lastly, I would say biochar is unique in that it offers affordability and scalability across all regions, right? We can envision smallholder farmers in Africa making biochar and making money at it. I'm not so sure you could say the same thing about bioenergy with carbon capture and storage, or direct air capture, right? Those are large scale, super high capex enterprises that really aren't scalable all the way from smallholder farmers up to large industrial operations. But having said all that, I think I got into this biochar business through food waste, researching food waste over the course of 15 years. And, we dream about the day in the future when we're at the sustainable state in human history where all the stuff that we currently call waste is now being utilized in some way. But the reality is that we're a long ways from that. So I think in the near term anyways, there's going to be enough waste to go around. So if we can fully utilize all the biochar systems and all the BEC systems, I think we'll be doing pretty well.
Yeah, thanks for that. Yeah, I like the idea of emphasizing co-benefits, right? Because obviously one of the concerns we're going to have is whether we're going to get sufficient demand pull, right? Even if we can develop the supplies for these products. And I also like the emphasis on where some of these CDR approaches fit for less developed countries and for smallholder farmers, right? Because if we're going to craft this portfolio, right, we're going to need to be feeding a huge number of sectors, right? So thanks for that. As you can imagine, we have an abundance of questions for this topic. So let me just launch into this and see how many of these I can make it through. So first question is states with the advent of algal mass from ocean warming, kelp farming, coastal seaweed harvesting, and other marine feedstocks, might not the feedstock supply for biochar leap by a few orders of magnitude? What is the upper bound? That's for any of you.
Yeah, I mean, I'm personally not that familiar with the potential for algal biomass. I know there's a lot of activity in that area, both in terms of microalgae and macroalgae. We have looked at macroalgae, also known as seaweed, of course, as a waste biomass resource for things like building products. And I know those numbers are absolutely enormous. So I think if you included that material in with all of the other things like agricultural residues and forest residue, we could definitely greatly expand the range of things we can convert to biochar. I don't have a good sense for what those numbers actually look like.
Okay.
And
Anybody else
I would just,
Wendy Lou?
yeah, I would just add that it would be interesting to also see if what the LCA would be in terms of the need for drying, etc., and then also transportation. But also to point that I'm aware of at least one project that's operating in Scotland that is testing, that's at sort of a pilot phase of using, I believe, some form of seaweed as the feedstock. So it is. I think it's happening on a small scale.
Okay. All right. Next question. Is this model based on a centralized approach where biomass residues are sent to a large pyrolysis facility and converted to biochar? Do you have data about small-scale biochar production and sequestration potential with smallholder farmers? So you've kind of addressed that before, but have you looked at it to that granular level?
Well, I guess I can kick it off. We did not look at individual biochar production equipment. We do envision that you would be able to do this all the way from, say, smaller kiln type systems that would be suitable for, you know, smallholder farmers or small communities, all the way up to very large scale systems capable of converting you know, thousands of tons a day. So in that sense, we don't envision this to be a centralized architecture. We think this would be more distributed at different scales. Of course, you would expect that there would be quite a range of different scales depending on the specifics of the actual economy. But yeah, I mean, we are aware of, you know, commercially available systems that are kind of continuous fed systems that range all the way from 1 ton a day up to several thousand tons a day. But even for batch systems, kiln systems, I think this would be viable, and we would expect that to contribute to it as well. I don't know, Wendy or David, if you wanted to add anything to that.
Yeah, happy to add a little something. So yes, I think the only assumptions that we made on the technology that we use is that it produces biochar at temperature of at least 600 degrees and that it produces the heat required to dry the incoming biomass. And basically that is the only assumption we made on the technology that is used to produce it.
Yeah. All right. Now, here's a question truly in the weeds or in the biochar. The correlations in your paper lead to biochar yields in the range of 35 to 50%. In a recent Air Miners webinar, a yield of 40,000 tons of biochar per 183,000 tons of biomass, or only 22% was stated. This means the byproducts yields are 1 to 4 times that of the primary biochar product. Do you have data to quantify good yields of CO2 compared to the rest?
I'm not sure where the person asking the question got those numbers, but we made several assumptions about mass yield of biochar. For agricultural residues, which were the bulk of the residues we identified, we actually assumed a dry basis mass yield of 25%. Okay, so that sounds like it would be more in line with the numbers that were mentioned. For some of the other feedstocks, the yields are higher than that, and that all of the references to literature sources are provided in the paper.
Okay. All right. So here's a question on methane, right? Let me pick through this and try to just summarize it. I think what the questioner is asking is, while they would assume that on tropical soils, right, you would see benefits in terms of methane sequestration, this wouldn't be true in areas such as Europe. So they're asking, why would methane ultimately be decreased across the board beyond only flooded soils?
I can try this one. Yeah, so we did not include any effect of biochar on methane emissions or nitrous oxide emissions from soils. But the basic idea of why biochar reduces methane emissions from soil is methane is produced through anaerobic condition, and biochar helps sometimes just alleviate these anaerobic bubbles in the soils, and so that decreases methane emissions from soils. So yes, flooded soils are the most rice cultivation, rice paddy soils. These are the most prone to this beneficial aspect of biochar application, but we did not include any of that in the analysis. Yeah.
I would just add, I mentioned that very briefly in my presentation as one of the benefits of using biochar in the context of the areas of agriculture in particular that we're trying to reduce methane emissions from, particularly animal agriculture, and as David mentioned, rice cultivation, as well as the use of biochar to reduce methane emissions from landfills.
Okay. Let's see. Biochar yield and properties depend a lot on biomass source and process conditions, particularly temperature. Do you see the need for regulation?
I guess I'm not sure what how regulation would.
Yeah, what didn't quite get that. How about the first part of it? Maybe just the fact that a lot of the yields and properties are dependent upon, feedstock, temperatures, soil composition, and et cetera. Is that all taken into account in terms of the analysis?
Again, we made some assumptions about mass yield. Agricultural residues were all assumed to have a 25% mass yield. Other materials like biosolids and manures, as I recall, had somewhat higher mass yields on a dry basis. Certainly mass yield is a function of temperature, but I think most of the literature, and we referred to a paper by Quick and Weber, which I believe was published in 2018. Their data shows that for both herbaceous and non-herbaceous biomass residues, once you get past the temperature of 600 degrees C, the mass yield is pretty constant, around 25%.
Anything else to add? Okay. Let's see. From a reporter with S&P Global, why is the U.S. investing in direct air capture, such as through 45Q instead of biochar, which is better in terms of bang for the buck? I don't know if you have an opinion on that.
No, Wendy, why don't how would you like to feel that one?
Yeah, no, I appreciate the question. And, I always want to preface any questions about different CDR technologies that the statement that we need all of them to work immediately at their full scale and potential. So I never want to pit any against each other. And I'll also say that this is purely speculation. Unlike the paper that we're presenting, I think it's hard to pinpoint exactly why there's currently more investment at the federal level in the U.S. for DAC in particular versus biochar. I do think that the industry is trying to be more visible, to educate and advocate at the government level, both for legislation as well as policy and funding that comes aligned with that. And I think, frankly speaking, the DAC industry has done that very well, and that is one reason for its inclusion. Tom, do you have anything to add, or David?
No, I think you covered it well. Thanks, Mary.
And Will, I mean, I know you are our host, but if you have any thoughts on that too, I'm certainly very curious.
Yeah, I mean, I think probably at the outset, a lot of what was incorporated in 45Q was driven largely by those that came into government and advanced CDR, right? And everyone has their priorities. I think it was probably one of the easiest at the outset to quantify, and so amenable to 45Q. But I think there's other things on the table, including biochar, that have a good enough MRV profile at this point to be included. And so hopefully they will in the future. Hopefully that was an opening salvo. Next question. So another methane question. They're curious why methane was not included in the analysis. They said, is it quantifiable? Is it potentially significant? I think they're implying that it could ultimately result in a net increase in methane, which I know is not your argument. But why did you opt not to assess either methane or maybe nitrous oxides in the study?
I can try that one. Yeah, so the methane emission reduction from soils, or nitrous oxide emission reduction from soils following biochar application, is very hard to quantify. It depends on the amount of nitrogen fertilizer that you would be applying, water level and water regime in the soil. And so that would have needed and required a level of granularity that we don't have and we couldn't find, basically. Now, other sources, there could have been methane sources from biochar production, but because we assumed a very dry feedstock, even from a low-tech pyrolyzer's point of view, there's a fairly recent paper that shows that the methane emissions from pyrolysis itself is extremely low. And if we consider an industrial pyrolyzer, then the afterburning and the syngas recovery would have prevented the emissions from methane. A potential other source that we have not accounted for is the methane emission reduction from avoiding piling of the feedstock. So that again makes our analysis fairly conservative. Yeah, but that's all I can think of. I don't know if Tom or Wendy Louie have something to add.
No, I think you covered it well. Thank you.
Okay. So a question for David. You previously published about how much sugarcane residues could contribute to emissions reductions in Brazil. What assumptions did you make about alternative uses?
Oh, thank you for that question. Yes, so in Brazil, sugarcane residue, sugarcane bagasse, right, is currently used to produce electricity. And so one of the assumptions that we had to do, if we're considering the use of bagasse for biochar production, is to kind of fill the hole in the electricity production of the region. In the case of the paper, we looked at Sao Paulo. And so that leads to, well, complicated assumptions, because you have to do that. You have to look at marginal electricity production and which type of electricity will cover the blank left by biochar production. So yeah, then you enter the realm of consequential or LCA, life cycle assessment, and you need to make a lot of assumptions. So yeah, this is the tough part of using a feedstock that is already used for some other uses.
Okay. Next question: are there any African countries actively promoting biochar at the farmer level?
Wendy, you want to?
Yeah. That's a very fun topic. I appreciate the question. So this will admittedly be an incomplete list, just sort of off the top of my head. I definitely point to Plant Village, which has several projects, not only in sub-Saharan Africa, but also other regions. And one of their interesting projects is using invasive plant species as a feedstock. So there's this additional benefit. And they're also working to bring carbon credits to the smallholder farmers as part of their projects. There is a Bio for Africa project, which is partially funded, I think, by the Denmark government, Danish government, and that has biochar as part of its work. There is also, and I encourage, I know we have a couple folks in the audience, and please feel free to add in others as you know of them as well. There is a company called Net Zero, which is operating in Cameroon and then also Brazil, and they're doing community-based biochar production that includes energy generation. So again, and there's also Biosora, which just opened a fairly large facility in East Africa. You can find a story on Carbon Herald about that, the media outlet. So I could go on and then want to talk about other regions, but suffice it to say that there are some very exciting projects, both at the smallholder farmer level up to community-based projects that are producing biochar and other social and environmental co-benefits.
Thanks for that. Next question. In dry regions, the cost and energy inputs to dry biomass could be much less, and they give examples of eastern British Columbia and eastern Washington. Would this offer a significant advantage to such regions for biochar production? Oh, Tom, you're mute.
David, would you like to take that one? I think that relates to the emissions associated with biochar production.
Yeah. Yes. I think it would. Yeah, definitely. Drying the biomass to a certain level is one of the big energy input that's required. So having a drier biomass at the start would definitely help. I think dry region could potentially also benefit more from biochar application to their soils. If we're looking at the global south, for example, where we know that side effects of biochar are usually higher in tropical and degraded soils than they are in temperate soils. So yes, definitely avoiding or preventing energy loss for drying the biomass could potentially benefit the net carbon capture potential of the practice.
Okay. Next question: is there some potential for use of biomass such as food waste from a consistent source to be used for production for biochar? How does that compare to alternative methods for organic waste processing, such as composting?
Yeah, I'll take this one because I've spent quite a bit of time working in the area. I would say, and this is based on direct experience, because we've made biochar from a lot of food waste. Food waste generally is a challenging feedstock for a number of reasons. One is very high moisture content. Just your normal post-consumer waste is typically 70 to 80% moisture. So that makes it challenging. Secondly, it's generally speaking is very heterogeneous, right? It especially post-consumer waste is very challenging. even if you're able to find, say, a food processing plant that has excess food waste available, it often varies in properties over time, right? And its availability can change as well. The last thing that's concerning about food waste in general is contamination. We have lots of situations now, at least in the US, where composting facilities and anaerobic digesters won't even take food waste because of concerns over primarily plastic contamination. However, having said all that, I think there's a big potential because of some of those issues I just mentioned. If you can get past the high moisture content, pyrolysis to make biochar may be a very good option. Because if there's a little bit of contamination, be it plastic, cardboard, whatever the case may be, we found that that contamination may not impact the properties of the final biochar. So although from a purist standpoint, you don't want any contamination, from a practical standpoint, small amounts of contamination that may make the material unsuitable for composting or anaerobic digestion may be just fine for pyrolysis. So I think as of right now, food waste is very challenging, but I think the potential is significant for that waste.
Thanks, that's helpful. Yeah, I know a lot of times we talk about this in the context of BECCS also, right? And I know there's some of the same sort of concerns, but it's interesting because boy, there's certainly a lot of it, right? That we would hope we could use and avoid some of the environmental impacts, at least in terms of BECCS of some of the alternatives like food crops. But that's interesting. Let's see. I think we have time for one more question here. The question is, I'm wondering how different the result of this paper would look if the impact of biochar on priming was included. Is there enough information to include these impacts in the framework?
David.
Yeah. Yeah, I'm happy to take that one. Yeah, so when we talk about priming, it's either can be a positive priming, which is an increase in the mineralization rate of native organic carbon in soil, or negative priming, which would be a decrease in the mineralization rate of the native organic carbon in soils. And as we were writing the paper, I was hoping that we could put something on priming there, but the truth is that all the current literature does not really agree. Some of them show a positive priming, some of them show a negative priming, some of them show a positive priming at the beginning turning into a negative one over time. So and although there's a slight like movement towards biochar inducing negative priming, which is a reduced in the mineralization rate of the native organic matter, they don't really understand why. So we don't have enough indication now of like what's happening. And so because of that, we couldn't put any factor on it or couldn't apply different rates towards different climate or soils. So we decided to exclude it entirely. Now, whether or not this could increase or decrease depends on what the future research will say. But we think it's a conservative approach to have not included it because of the trends towards negative priming following biochar application. So yeah, definitely an interesting topic, one to follow.
Anything to add on that, David or Wendy Lou?
No.
Okay. Well, we are almost at the top of the hour. Any final thoughts in terms of moving forward in research or anything of that nature?
Wendy Lou, you want?
Well, I mean, I'll just make my usual pitch for there to be as much applied research as possible that can really help the industry grow both on the equipment side. There was a question around permanence, although I think that the body of research is actually quite robust for that. And then I was just going to say, last comment before I hand it over to my co-panelists, that if anyone would like to do a deeper dive into biochar, we've just finished our annual virtual conference, and I'm going to put a link to the recordings in the chat in case anyone wanted to access them. Or and also please reach out if you have projects or any questions about IBI.
All right. Thank you, Wendy Lou. Anything else, Tom or David?
I guess I would just like to advocate for more research and industrial uses of biochar. Of course, most of the literature is really focused on agriculture and soil health. Right. But we're at RIT, we're very interested in manufacturing applications, things like just using biochar to replace carbon black. You can think like tires that use huge amounts of carbon black. Well, we think at least part of that could be replaced with biochar. And if that was the case, that would become a huge market for biochar overnight. Even though it's not a long-term permanent solution, it would help us grow the biochar markets. So we really want to help develop and expand industrial applications for biochar.
Yeah, I think that's a really ripe area for additional research. So thanks for that. So we are at the conclusion. I'd like to once again thank all three of our panelists, Tom, David, and Wendy Lou, for joining us, and everybody in our audience for excellent questions as usual. And we'll hope you'll join us again in the future. We should be back on in December with a couple of episodes, and hope to see many of you. So once again, thank you to everyone, and goodbye now.